monitor closely. Where's Borme? The first couple minutes and make sure the sound's coming through.
Yeah.
So, you know, you get to drag something over that.
Yeah.
Yeah.
Make sure we're on the same page. Okay.
Yeah. Okay.
Okay, it looks like the mic is working.
Yeah, I think it's okay.
That's
I'll
good.
check.
It's taking a second to load.
I get the lighting.
Is that here?
Shoot.
Whose voice is that?
That's us. That's us.
That's us like 5 minutes ago.
I know. Oh my god.
It's not starting yet. Why? That was me like 1 minute ago.
All right. Oh, I think, is it working now? Okay.
Okay, we didn't do anything. Just don't touch it.
I just, yeah. But it sounds like something is.
Yeah, I can see the bar. Okay, apologies to everyone who missed the very beginning. Okay, I'll step back to the beginning of the slide, I guess. Okay. Whoops. All right, great. So we're going to start our evening thinking about how we can take brains with atypical neural activity and push them towards healthier patterns of activity. Our brains work by sending electrical signals between our brain cells called neurons. In many neurodegenerative and neuropsychiatric disorders, those electrical signals stop working properly, leading to symptoms that range from the tremors in Parkinson's disease to the hallucinations in schizophrenia. A growing field of neuroscience called neuromodulation aims to bypass these malfunctioning electrical signals by inducing healthier brain signals. And there are a lot of ways that we can do that. One of the most successful treatments, called deep brain stimulation, or DBS, has been used to stimulate the diseased parts of the brains of patients with Parkinson's disease. The patients undergo neurosurgery to have electrodes implanted in their brain, and regularly stimulating those electrodes can help patients with their tremors and improve their quality of life. But neurosurgery isn't the only answer. Today, our first speaker, Dr. Desmond is going to talk to us about another method called TMS that doesn't require electrodes be implanted in the brain. Instead, a magnet is placed over the head so that it can manipulate the electrical activity in the brain, with the hope that a treatment like this could be used to help people with disorders like PTSD or depression. Now, all of this might sound a lot like mind control, but Desmond is going to walk us through exactly how TMS works and why he thinks that is such an interesting new tool in his talk titled Neuromodulation is Not Mind Control. Neuromodulation uses a lot of very cool tools and techniques, but we don't need any extra equipment to experience neurosci-fi. In comic books and movies, we see people who get superpowers through things like exposure to radiation or spider bites. But we all have our own personal superpowers that don't require quite so much drama to become activated. In fact, we're all using them right now. Our superpowers come from our central nervous system, composed of our brain and spinal cord. Our central nervous system snakes throughout our body, spending its day effortlessly coordinating many of our bodily functions. So what happens when it stops working properly? For our second lecture of the evening, Dr. Veronica is going to walk us through how studying what happens when we lose some of these superpowers through spinal cord injury can teach us a lot about the amazing things our central nervous system does every day. And in doing so, she'll show us that we don't need anything extra to be extraordinary. For our last talk of the evening, we're going to move outside the brain. So we've all probably had the experience of laying on a couch with the remote just out of reach, and you wish that you had telekinesis and you could pull it toward you instead of having to get up and grab it. Or maybe you felt jealous watching a movie like Matilda or the X-Men as the characters effortlessly manipulate the world around them using nothing but their mind. But fictional characters are not the only ones harnessing their brain power to move things around. For decades, neuroscientists have worked on developing a technology called a brain-computer interface that records neural activity in real time and uses it to do amazing things like moving prosthetic limbs. Brain-computer interfaces work via an implant in the brain that records the neural activity. That neural activity is then fed to a computer where it's transformed into things in the outside world. Brain-computer interfaces have already been used to do amazing things like help paralyzed patients move robotic limbs or type words out onto a screen. And with Elon Musk's new Neuralink initiative, there's a lot more attention on this really important research. But brain-computer interfaces can do a lot more than just manipulate prosthetics. They can give doctors important information for things like seizures and brain injury recovery. And they could even be used to stimulate the brain. So to wrap up our day today, Dr. Brian Litt is going to tell us more about how this technology works and share some of his lab's own efforts to utilize this technology to help patients with seizures. And because this technology is becoming more pervasive, he's going to challenge us to consider the ethical implications and to ask ourselves whether what we can do is what we should do. So today we're going to hear just a little bit of the amazing research that's happening in Philadelphia and around the world in neuroscience. But we're very excited to have you all here. So with that, let's begin our journey into the world of NeuroSciFi.
Sorry, I don't see the speaker notes, so I'm going to go off of my phone. Thank you all for coming. Our first speaker today is Dr. Desmond Oates. Dr. Oates is the Associate Director of the Center for Neuromodulation in Depression in Stress and co-director of the Penn Brain Science Translation, Innovation, and Modulation Center at the University of Pennsylvania. He is an assistant professor in psychiatry and a staff psychologist seeing patients at the Center for Treatment and Study of Anxiety. He mentors PhD students in the Department of Neuroscience and is part of the Neuroscience graduate group at Penn. Dr. Oates' research combines brain imaging with brain stimulation to understand how information travels through the brain. He uses insights from this basic research to develop novel brain stimulation treatments for neuropsychiatric populations. Dr. O's research has been funded by institutional, foundation, donor, and National Institutes of Health grants. Please give a warm welcome to Dr. Oates as he takes the stage to give his talk entitled, Neuromodulation is Not Mind Control. Yeah. Yeah, this is also here.
Oh, yeah. Thank you for having me. Thank you for being here. I'm excited to talk about my research and brain stimulation in general. This talk title is a lie. I've controlled your brain since you've been coming in, and you're going to donate piles of money to my lab. So sorry about that. I'm just warning you ahead of time. So I focus a lot on TMS, and I'm going to explain a little bit why I do that, why that's my favorite brain stimulation tool. It's been around for quite a while, and so it's there's something convenient about firing these pulses, which is use electricity to generate these little magnetic pulses that carries information through the scalp and skin without getting kind of stuck up there, and generate some little electric pulses right under the TMS coil. So we have some control over that. And it's the magnetic field that carries that information down into your brain, but the activity that it causes is electrical activity, like what usually happens in your brain when you're controlling movement and having thoughts. So we fire these brief magnetic pulses, right? And we depolarize or activate the neurons that are underneath it, these brain cells. And we can also, besides just doing a pulse here and there, we can create these trains of stimulation, and we call that repetitive transcranial magnetic stimulation, which means we fire it in kind of a sequence, and depending on the kind of sequence we use, we can have different effects on the brain, and sometimes cause it to be more active or cause it to be less active. So that gives us some a degree of control, which pans out in interesting ways. One thing that it is not is shock therapy or electroconvulsive therapy, which there's a lot of stigma against it. But if you're trained in psychiatry, you actually realize that this is one of the best treatments out there. It's an extreme lifesaver. It's really, really amazingly powerful for a very, very sick population, subset of the population with mental illness. But that's not what I do. Some of the downsides of that
think we're going to do questions at the end.
Okay.
Yeah, thank you. It's working. Yeah, I think it's, yes. Okay. Oh, and we get to reshare this. Or there's nothing on there now. Yeah, I know. I'm trying to.
Do you turn presenter mode? Wait, no,
It is
he's gonna do it. Thank you, Dr. Oates, for the very stimulating talk. Our second speaker is Dr. Veronica Tom, a professor of neurobiology and anatomy at Drexel University. Her lab studies spinal cord injury with the goal of identifying potential therapeutic targets that will ultimately help restore function in people living with spinal cord injury. Dr. Tom has a neuroscience degree from New York University and received her PhD from Case Western University. Throughout her career, she has made innumerable contributions to our understanding of axon regeneration following injury that has been funded by several agencies, including the NIH, the Department of Defense, and the Craig H. Nielsen Foundation. Dr. Tom has received numerous fellowships and rewards, acknowledging her outstanding record of research, teaching, and mentorship, including the Julian Marsh Faculty Scholar Award from Drexel University, and her selection for the prestigious Hedwig von Amerigen Executive Leadership in Academic Medicine Fellowship. Please give a warm welcome to Dr. Tom as she takes the stage to give her talk entitled, Who's the Boss? Reflexes and Dysautonomia After Spinal Cord Injury.
Thanks very much. I can barely see over this podium. So thank you to the organizers for the invitation. This is a really cool opportunity to share some of the things that we are doing in the lab and as the spinal cord injury field, research field in general. So, okay. Oh, that's just another title slide. So a lot of what we think about when we think about the CNS and the brain and the spinal cord is thinking about really high level functions, right? So we think about things that make us uniquely human. So this is really nicely captured in this fantastic movie Inside Out, where you have the brain controlling various aspects of emotion, cognition, memory, learning. And those are all really important things to study and to consider. But there are other things that the CNS controls that's not as high level, right? So things like movement and sensation, critical things toward shaping our experience in the world, but not at essentially at the level of emotion or cognition. And when you think about things even more basic, the CNS also controls really fundamental functions of our entire physiology. So things like modulating blood pressure, immunity, kidney function. That's just to name a few. I'm just highlighting those because I'm going to touch upon them in my talk. So how is all of this possible? So we have to consider that the CNS is modulating the sympathetic nervous system. It's not quite sexy, but there you have it. And so we have, let me see if I can you see this mouse? No. Is there a way?
Yeah.
Oh, wait. You see it? Oh, okay. Oh, that's going to test my spatial skills. Okay. So if you look at, so these are all of these peripheral organs, effector organs that are innervated by the sympathetic nervous system. So they're innervated by neurons within the sympathetic chain that's out in the periphery. Right, so this is the peripheral nervous system, but these neurons are modulated, directly synapsed upon by neurons within the spinal cord. And these neurons, I'll talk about the circuit a little bit more in more detail, but these neurons basically control a lot of the function of these neurons and drive innervation to these effector organs. Let me see if this works. Sorry, technical difficulties here. Okay, so what role does the CNS play in regulating sympathetic nervous system or the sympathetic function? And so kind of the classic model of understanding what a structure does is to know and see what happens after that structure has been lesioned or injured, right? And so we have something like that when we have a spinal cord injury. So spinal cord injury, when you think of someone with a spinal cord injury, you often think of someone who's in a chair. So the first thought probably is this person is paralyzed, and depending on the level of injury, that's the extent of the deficits, right? So lower level injury, you'll have paraplegic. Higher level injury, more of that descending input from the brain to the spinal cord is lost, and you'll be more likely to be quadriplegic depending on the level of injury. But what's really important to consider is that the leading causes of mortality and morbidity are all related to things that are affected, sympathetic functions that are affected after spinal cord injury. So you have susceptibility to infection. That's one of the leading causes of mortality. Issues with circulatory system, as well as issues with the urogenital system. And we think that kind of key underlying causes for why these individuals are susceptible to these infections and to these disorders is because of a disrupted sympathetic nervous system. So if we go back to the schematic, we have all of these effector organs that are innervated by sympathetic neurons out in the periphery, but these neurons are regulated by neurons within the spinal cord. And so it's not hard to imagine that if you have an injury within the spinal cord, you're going to affect activity of these sympathetic neurons. And depending on the level of the injury will really impact how much disruption of the sympathetic system you have. So let's step back. How is that possible? So we'll step back a bit and think about the system as a circuit, as a really simple reflex circuit, right? So we're all familiar with, you tap the knee, that's a sensory stimulus that's coming into the spinal cord, synapses and activates either one or two neurons. There are also monosynaptic connections. And then you have these motor neurons that innervate the muscle. Those fire, and you get the leg kicking out, right? So it's a very simple reflex circuit that is really fast and importantly does not need the brain, right? You don't need the brain to see this reflex. So there's something that's very similar in the sympathetic system where you have neurons. You have input neurons, sensory information coming into the circuit that's relayed up to these output neurons that are, depending on the level of the cord, they're in kind of T1 through L1, L2. Those project out, they synapse upon sympathetic postganglionic neurons, which then innervate the effector organs. It's a lot of specifics, but basically the take home is that this motor reflex circuit is recapitulated or mimicked by the sympathetic reflex circuit. Sensory information comes in, output out to the periphery. In this case, instead of the muscle, we're talking about effector organs. So as I said, all of this, you don't need the brain to actually see these reflexes occur. However, the brain does modulate these reflexes. So there are inhibitory connections that basically tone down activity of the circuit, right? So what happens when you lose that circuit after a spinal cord, or you lose those modulatory projections after a spinal cord injury? Well, you lose a lot of this inhibition. And so what does that actually look like? So if you remember, the sensory information is stuff that's activating the circuit. If you give a sensory stimulus such as colorectal ascension, which mimics constipation in individuals, which is a common problem with people with people with spinal cord injury, you see this dramatic activation of the circuit, right? This is basically now a hyperexcited, overactive reflex, and you'll get this really sudden and extreme increase in blood pressure because you have significant vasoconstriction, activation of the sympathetics, you get norepinephrine release, and that causes vasoconstriction. And so this is what, in real life, what heightened activation of this circuit means. You also get compensatory, most of the cases, compensatory bradycardia, but that's through the parasympathetic system that's intact. So if you look at, just to give you kind of a contrast, if you look at you give the same nasty stimulus, but to an animal, in this case, with either a lower level injury, so more of the descending input to this circuit is maintained, or an incomplete injury, so still more of this level descending input is maintained, you get a slight bump in blood pressure, but it's not nearly as dramatic. And that's because you have enough of this brain input to basically tell the circuit to chill out, right? So just as an analogy, if you have this kind of relatively infantile circuit below the spinal cord, this reflex circuit that is normally held in check by the parental unit, the brain, you have things that are it's a very happy, well-maintained, well-controlled situation. If you lose that parental unit, right, the spinal cord or the brain input down to the spinal cord, this circuit is now left on its own devices. And as you can see, they can wreak havoc, right? So this is a real picture of what my kids did when I turned my back when they were much younger. But that's essentially what's happening with the sympathetic circuit when you lose that modulatory input from the brain. Things are going a little bit haywire. So we have just this quick summary of what I've talked about. You have a high-level spinal cord injury. You lose that brain regulation of the sympathetic nervous system. That results in heightened sympathetic reflexes. That results in effector organ dysfunction. We talked about the cardiovascular system, right? So you have increase in blood pressure. I'm not talking about it here, but there's also vascular remodeling. That's not great. So the sympathetic nervous system innervates many organ systems. Think about that, one of the first slides that I showed you. So how does sympathetic hyperreflexia, these overactive sympathetic reflexes, impact other effector organs? So let's talk about another effector organ, the kidney. So this is kind of kidney for dummies, which is part of my speed. So the kidney is a highly vascularized organ, right? It's really important because it filters out all of this garbage out of your blood so that you basically have a nice, healthy, well-maintained homeostasis in blood. So you have unfiltered blood coming in, it gets filtered through the glomerulus and all the crap comes out, and then basically the blood gets recycled and all the garbage comes out of the kidneys through the urine, right? But because this is such a highly vascularized organ, you need to be able to maintain the amount of blood that's flowing through it. Okay, it's a really kind of neat intrinsic homeostatic mechanism to basically maintain kidney integrity. So because there's so much blood flowing through, it'd be highly susceptible to any damage through increases in blood pressure. So if you look, this is just a cartoon of a homeostatic process called autoregulation, where kind of in this physiological window of blood pressure, if you go increasing in the amount of blood pressure, you actually have more vasoconstriction. So that decreases the amount of blood that's flowing through the kidney to basically limit how much blood is going through the kidney at one time, right? To keep it at a steady state. So that's a really important mechanism to maintain the health of the kidney. So we looked at kidneys in animals that had a low level, so a thoracic level 10 spinal cord injury. So these animals do not experience sympathetic hyperreflexia. And you can see that when you look at the autoregulation response, that increasing changes in blood, so if you increase systemic blood pressure, you actually see a curve that's very similar to what I just showed you, where you have this dampening of, you have constriction to restrict blood flow that's going through the kidneys despite this increase in blood pressure. When we look at animals or kidneys from animals that have a high level of spinal cord injury, so these are the animals that experience that hyperreflexia, so those extreme periods of hypertension, you actually lose this homeostatic response. And so when you increase blood pressure, you don't have that vasoconstriction to limit blood flow, and blood is essentially pouring into the kidney. So remember, this is a protective mechanism to maintain the integrity of the kidney. So what does that mean? So this is in collaboration with a buddy of mine who's now at Case Western, and we looked at the kidneys in these animals. So this is a kidney of an uninjured animal. We stained for collagen, which is just connective tissue, but it's an indicator of fibrosis within the kidney or scarring. You can see that compared to a kidney from an uninjured animal, kidneys from these T3 spinal cord injured animals that experience these multiple bouts of hyperreflexia, sympathetic hyperreflexia, and these periods of extreme hypertension, and don't have that autoregulatory response, have a lot of scarring within the kidneys. And it's not something that's actually just specific to spinal cord injury. So if you have a low level injury where those animals don't experience these periods of sympathetic hyperreflexia, you see some collagen, but I didn't show the numbers, but this is significantly more scarring. So it's not an injury. It's not a peripheral response. This is something that is driven by damage to the central nervous system. So we talked about how spinal cord injury will affect both the vasculature as well as the kidneys. We're also going to think about the spleen, which is an important organ for mediating immune function, right? So if you look at animals, so this is all from rodents. This is a spleen from an uninjured animal, and you compare that to a spleen from an injured animal 8 weeks after injury. You can see that the spleen is from the high-level spinal cord injured animal. So these are animals that experience those repeated bouts of sympathetic hyperreflexia, right? That unchecked circuit. There's dramatic splenic atrophy. So you have the spleens are smaller, you have fewer splenocytes. And what does that mean in terms of immunity? So we wanted to directly test that. So we took animals, we squirted a little bit of Streptococcus pneumoniae into their lungs and looked just to see how well they did. So uninjured animals, when you give them that infection, they get sick, as indicated by a drop in body weight. So they weren't feeling great. But those animals recovered within a few days, and they got back to their baseline body weight. And all of them survived, as long as we looked at, which is 10 days after the infection. When you have an animal with a high-level spinal cord injury, so these are the animals with that unchecked sympathetic circuit, right? And do the same infection challenge, see those animals get remarkably sicker. So they lose dramatically more body weight. And in fact, we actually had to euthanize a few of those animals because of the weight loss criteria that we set off, or that we put in our ICOOK protocol. When we pulled out the lungs from these animals after the infection, so this is 10 days after the infection, and cultured them on blood agar plates, just to see how much residual bacteria was in the lungs. In the uninjured animals, there was some bacteria, but a lot of it was gone, especially when you compare it to an injured animal. So these are the animals that actually made it out the 10 days, that survived, but they're still pretty sick. So this is all of the residual. There's still a lot of residual bacteria within their lungs. So these animals, which have the splenic atrophy, that dysregulated sympathetic circuit, are not able to clear infections as well. So just to summarize a little bit, high-level spinal cord injury, you lose regulation of the sympathetic nervous system, get these heightened sympathetic reflexes that result in effector organ dysfunction. We talked about the vasculature, the spleen, as well as the kidney. So one thing that we have to think about is that we and others have found that over time, these heightened reflexes actually get worse. So these things are getting more severe. So it's not just loss of the descending input. That is an important cause for sympathetic hyperreflexia, but there are likely other factors that are at play. And so, we think that if we start to understand the mechanisms that actually underlie the development of sympathetic hyperreflexia, or these heightened sympathetic reflexes, irrespective of the loss of descending input, that may shed light on therapies that we can actually target to improve health for people living with a spinal cord injury. So one of the things that we started to think about was neuroinflammation. So neuroinflammation is associated with hyperexcited neural circuits, and it's been linked to other pathologies that are associated with hyperexcited circuits, and the degree of neuroinflammation correlates with pathology severity. So we looked at microglia, which are the resident immune cells within the spinal cord, and this is months after a spinal cord injury, and this is in tissue below the level of injury. You can see that the microglia are still highly reactive. Even in tissue, this is far remote to the injury. So if we have the injury at thoracic level 3, we've seen these activated microglia within lumbosacral spinal cord months out. And interestingly, we also looked at levels of soluble TNF, or tumor necrosis factor alpha, which is a master cytokine. It drives a variety of expression of a variety of different other cytokines, and that's also been linked to neuroplasticity. And when we look at this lumbar, or actually any tissue below the level of the spinal cord, even months out, we see elevated levels of TNF. So then we wanted to know, okay, we know, does inhibiting TNF, we have the players there. If we inhibit it, are we able to attenuate these hyperactive reflexes to improve and to diminish the detrimental consequences to effector organs? So this is just kind of a quick summary of a lot of work that a highly talented graduate student who's now in scientific consulting did. So if you look at kind of hypertensive responses in response to a noxious sensory stimulus to drive that reflex in injured animals that were treated with the vehicle, you can see that we get these dramatic increases in blood pressure, which is what I described before. If we continuously infuse a TNF inhibitor into the cord, or into the CSF, we actually, and in response to this nasty stimulus, you still see a response. So there's still some hypertension. So this is, I'm sorry, I should have mentioned, this is blood pressure. So this is millimeters of mercury. So this is all beat to beat blood pressure, and this is the mean arterial pressure, this line. You can see if you just compare the traces, this blood pressure trace to this blood pressure trace, you can see that the response is blunted, right? So there is hypertension, but it's not nearly as severe in the animals that were treated with the TNF inhibitor than the vehicle-treated animals. So we see diminished sympathetic hyperreflexia. How does that translate to the other effector organs? As I mentioned before, there's splenic atrophy after these high-level injuries where you have dysregulation of the sympathetic circuit. When we squirt in the TNF inhibitor, we see almost a normalization of splenic weight and more normal numbers of splenocytes within the spleen, which suggests that these animals have better immune systems. Does this actually translate into improved immunity? So we went back to that infection challenge that I described earlier, right? So those uninjured animals, that they get sick. The injured animals that are controls get much sicker, and some of them have to be euthanized. There's a lot of lingering bacteria within their lungs. And when we look at the animals that were injured, but that were treated with this TNF inhibitor in the CSF, you can see that those animals got sick, right? So they still lost a lot of body weight, but remarkably, none of them had to be euthanized. They all survived till the 10-day post-infection monitoring period. And when we pulled out their lungs and put them on blood agar plates, we found that there is some residual bacteria, but it was dramatically less than what we saw in the injured controls. So this is just to summarize everything. So if you have a high-level spinal cord injury, you have enough disruption of brain input to this sympathetic circuit below in the spinal cord. There's neuroinflammation, probably other factors that we're starting to look at as well. That all results in heightened sympathetic reflexes, that results in effector organ dysfunction. And hopefully by targeting or understanding what these mechanisms are, that we can target them, we can improve, diminish some of these heightened sympathetic reflexes, and hopefully mitigate some of that dysfunction in the effector organs. So this is the most important slide. This is just a thank you for all the people who did the work. Some of them are not pictured. This was our first lab activity post-COVID when everyone felt comfortable again. So I'd like to thank basically everyone for being such a great group and letting us be as successful as we are. And then I'd also like to thank members of the Marion Murray Spinal Cord Research Center. It's a great group of collaborative faculty and investigators who are all focused on various aspects of spinal cord research, injury or not injured, as well as the funding agencies. Thank you.
Apologies, but I forgot to mention earlier that there will be a general Q&A session at the end with all three speakers. So hold your questions until the end. Our next speaker is Dr. Brian Litt. Dr. Litt is professor of neurology, neurosurgery, and bioengineering at the University of Pennsylvania and director of the University of Pennsylvania Epilepsy Center. He is one of the world's leading authorities on neuroengineering, implantable brain devices, and neurotechnology, particularly for epilepsy. A clinician scientist, inventor, and entrepreneur, Dr. Litt divides his time between directing the Penn Epilepsy Center, Penn Center for Neuroengineering and Therapeutics, Penn Health. Sorry about that. As I was saying, Dr. Litt divides his time between directing the Penn Epilepsy Center, Penn Center for Neuroengineering and Therapeutics, Penn Health Tech, a new university-wide effort to bring new technologies from Penn scientists to patients, and his Philadelphia startup, Blackfin. Dr. Litt has an engineering degree from Harvard, received his MD and training in medicine and neurology from Johns Hopkins. Dr. Litt has received numerous honors and awards and also serves as an advisor to the NIH/NSF/White House Brain Initiative. He has mentored over 50 graduate students and postdoctoral fellows who now serve as leaders in academia, industry, and government worldwide. Please give a warm welcome to Dr. Litt as he takes the stage to give his talk entitled Ghost in the Machine, Melding Brain, Computer, and Behavior.
Or just a PowerPoint. Yeah.
Or is it?
Probably here somewhere, right? This is the one that's on your machine. There's another one. That's the one.
Okay, wait, you have to close out this one first, though. Can you just
Close that one.
Oh, no, click here. It's still open on the screen. You have to close this one. Great. Okay. We should be able to go back.
Great. Well, thanks so much for inviting me to speak today. So a couple of teaching points before I get started. If somebody asks you to submit a bio before you give a talk somewhere and you don't do it, then they give you a full introduction like that. The longer the intro, the closer you are to like retirement and death. So I would have preferred like he's a faculty member here. A couple of quick things. I don't direct the Epilepsy Center anymore. Kate Davis does, and Blankfin is bankrupt. So besides that, everything is good. So, but I am still employed here, and several of my graduate students, a bunch of them are here out of the kindness of their hearts. Usually they sit on the Zoom when I like give my lectures for my class, and they're like, stop, shut up. Don't say that. All right, so we're going to have a little bit of fun, and we're going to start with a story. So a 30-year-old veteran walks into a bar. I always wanted to start a grant with a man walks into a bar. This is the beginning of a grant. None of the patrons are aware of the anti-seizure device implanted in his brain or the traumatic brain injury that requires it. It's been a long day. He quickly downs a cold beer. Within minutes, his iPhone vibrates with a text from his implantable. What are you doing, Dave? Your probability of seizure within the next 12 hours just increased to 64%. 20-ounce beer, he texts back. The device pauses, replies, then resumes. I'll remember that. I suggest you not have another one. I'll stimulate for now and text if things worsen. Above 80% probability you should take an Ativan and call an Uber. So how realistic is that? Like, could we actually do that now? Would somebody give you $7.5 million based on that paragraph? They're not as smart as we think, are they? So brain-computer interfaces have captured our imagination in a lot of ways. They've captured our most serious scientific endeavors. I mean, well, actually, so like Homer Simpson isn't our most serious scientific endeavor, but they've captured our imagination in our humor, in our science fiction. I'm not exactly sure why for brain-computer interfaces you need to plug into their lungs, but that might be for the last speaker. And some of the most breathtaking technologies that we have going, including this, and we won't talk too much about this. Well, maybe a little bit. I'm not going to give too much credit to the financial sponsor, but his name rhymes with Pelon Dusk. But so these are important, interesting discoveries, and they've really, over the past 20 years, evolved dramatically since Matt Nagel was the first human implanted with a brain-computer interface to use to control a machine. So these are used for a lot of things, and you've all seen the videos of monkeys moving and feeding themselves marshmallows by controlling robotic arms through implants in their motor cortex. You've seen maybe videos of people with paraplegia driving cars with 2 or 3-dimensional brain-computer interfaces. Makes me a little nervous. That's how they got there to begin with. Sorry, that's really in poor humor, maybe, but it's amazing what things can be accomplished. But I'm partly a clinician and partly an engineer, and my interests are really bringing these things into everyday practice with neuro devices. There are a lot of disorders that we address, and here are some of the most common ones right now, where brain-computer interfaces, kind of writ large, devices that interact with the nervous system in open or closed loop using novel strategies, can be used to control. I focus on epilepsy, but you've already heard the last 2 speakers working on other things like spinal cord injury, mental health. How do we get signals out of the brain? Well, a lot of this work started with some of the early work from Penfield and Jasper, maybe in the 60s and 70s, where they put electrodes in the brain in the operating room, but then later implants that come out of the brain are externalized to map where seizures go.
We have a really active program here with a 12-bed epilepsy monitoring unit up on the 9th floor in the new hospital. And if you haven't visited it, you should come and visit us. Your IDs won't let you in, but I'm inviting you anyhow. Where we actually have state-of-the-art machines from BlackRock that can record at high bandwidth, process and stimulate in almost real time. We extract data through electrodes implanted in the brain, and we do quantitative measurements. And our lab focuses on a variety of different areas, but one of them is perhaps mapping surgical epileptic networks to figure out where to operate and intervene. The devices that are used currently in practice right now are relatively crude. They're kind of threshold detectors that work in the moment. So they might pick up a feature exceeds a threshold that says maybe a seizure starting, and it triggers an electrical stimulation in a very patterned way. It might be an open loop device that just stimulates deep in the brain, subthalamic nucleus, for example, to improve motor function in Parkinson's disease. They don't really communicate very much with the outside world. They may be able to telemeter data out, but it's limited variably depending upon the model, and there isn't really an ongoing dialogue. They're programmed relatively rarely. These patients may go to see their physician at 3-month intervals to get them uploaded. Not a time scale that's really conducive to real-time improvement or being informed about what's going on in your brain. And they don't learn. Despite that fact, over 3.5 million individuals in the United States have implanted medical devices that do detection, warning, stimulation, other functions. And these are just some of the examples for brain stimulation. You've already seen, examples of thalamic stimulation, cochlear implants, devices for pain, for spinal cord injury, for bladder function, and more recently, functional electrical stimulation for movement, stimulating neurons in the spinal cord or lower motor neurons that help people stand and even ambulate in a relatively crude sort of zombie-like function. But those things are improving as there's longer battery life, better processing power, more intelligent algorithm. Those things are improving, and they're improving at a pretty dramatic rate. So there's an explosion in BCI technology right now. And a lot of it's going on at Penn. There's hardware and materials, cloud computing, intelligence, algorithms, data science, natural language processing in the electronic medical record. And we'll talk about why that's important in a moment. The question is, how far are they going to evolve? And how far are you going to let them evolve? And what kinds of societal decisions are we going to have? So let's talk about some of those. Now, you notice that the speakers have different approaches to things. So poor Desmond is like seeing people who are depressed and anxious, and you could tell that his talk, he conveyed some of that to you. People with young children convey the excitement of having young children. I have people who are kids who are past their teenage years, so I'm going to talk about a dystopian existence. Not completely. So what sorts of technologies are there? Well, here's the question. Avatar was a great explanation of what we need. We need to be able to tap in, record, and be able to stimulate every neuron in the brain. We need to do it through a connector that's in the tail of a blue person, and then we need to transmit it through outer space into Sigourney Weaver's head. That makes sense. We can't quite do that yet, but we can do a lot. So the first thing is that there are new implants that are on dissolving silk that can meld into the surface of the brain and match the mechanical impedance of the brain to transmit over long periods of time. They're high resolution. By the way, the little Penn emblem are things that have been invented at Penn. This one is a single 1 square centimeter electrode with active electronics developed in the CNT that can transmit, record, and in the future and soon be able to stimulate really finely patterned electrical stimulation and zoom in and zoom out. Now, the first experiment by this student, who's now almost a tenured professor at Duke, called me in the middle of the night and said, I just wanted to let you know everything's okay. And I was like, what do you mean everything's okay? And he said, the fire only lasted a really short time. So it's just one of those great PI calls from a graduate student, because when you have active electronics on a sealed device and it generates heat and the lamination comes off and it hydrolyzes water into oxygen and hydrogen with a little bit of heat, that doesn't go so well. But these have improved a lot. Neural dust. These are piezoelectric devices that are activated by ultrasound that can turn that energy into electrical stimulation non-invasively or read out electrical activity. Science fiction? No, the company's called IOTA, and it's out of Berkeley and UCSF. Dissolving electronics, developed here, Flavia Vitale, our lab, and John Rogers at Northwestern. Optogenetic stimulation in fibers, which can go down to the submillimeter level. Electronics from Flavia Vitale that can be steered once they're in the brain and penetrate with 10 micron fibers using the same technology that mosquitoes use to inject electrodes in you, or actually not electrodes, but to be able to eat. Injectable electronic meshes from Harvard. And then, of course, these devices from Neuralink, and we're going to talk a little bit more about those. So the hardware is evolving rapidly. And finally, Casey Cullen's work with growing neuronal constructs that can be implanted and controlled with optogenetics, so that you're actually building new devices that will grow into the brain. Sounds sort of like one of those science fiction movies that doesn't end well, doesn't it? So far, Casey's doing fine, and his company just received $40 million in startup funding for that technology. All right, so what about the Neuralink device? What does it do? 20 micron fibers, multiple contacts on each wire, threaded with the brain sewing machine. Have you guys seen this? How many of you have seen these videos? How many of you saw their broadcast like 3 days ago on TV? It's like terrible when the person who provides the money presents the science, because you sit there and you're like, no, that's not what it does. But take a look. So it shines light. Actually, is the video going to work here? Shines light, figures out where the blood vessels are so it can avoid them, injects the electrode, comes back and moves to inject the next one. And their yield for single units off of these fibers is tremendous. They have wireless rechargeable. Right now, it's estimated about once per day that can transmit out data at very high rates and hundreds of channels at a time. And by the way, one of the founders of this company, Neuralink, is Paul Marollo, who was a PhD student of bioengineering. So that's pretty cool. But not every device that's being used right now is a Neuralink device. They're looking to get FDA approval for their first human implants. Now, they've changed a lot because they were going to augment people, to expand your thinking with all of the potential ethical conflicts involved in having a superior class, mostly rich people, who can be augmented while the rest of us kind of slog around in the laboratory. But there are a lot of devices that are really moving forward pretty fast. So monitoring electrode devices that are wireless, that transmit out from under the skin and the scalp, and there are a variety of companies doing that. There's the NeuroPace device, which is closed loop, which records, monitors EEG, and stimulates to shut off seizures. These are being linked to wearables, devices to predict events like seizures from NeuroVista, Bluetooth devices to monitor all sorts of biological signals, and they're now being linked to implantable devices. So not only do you look for a seizure pattern that looks like it's going on in the EEG, but to distinguish that, you can look and see if there are movements that are characteristic of that seizure. You can titrate stimulation in implantable brain devices for movement disorders, and you might give different stimulation patterns with steerable electrodes like the ones from Boston Scientific, which can steer the field to different areas. And you might say to your device, you know, I'm going for a walk, improve my walking, and I don't care about it. But you might say a different thing and have a setting and say, I'm going to sit down and write a letter to my children. So I don't care about my walking, but improve my tremor and don't let me worry about it. And these things are possible now through research here and in places like UCSF where Phil Starr is working. Probably one of the most important developments is our group and others are taking data out of these devices and putting them up to the cloud. So this is work in collaboration with the Mayo Clinic, and Brittany Scheid worked on this from our lab, where we have RC+S devices that can transmit data out in dogs, where we're taking those data out of the dogs and up to the cloud. We're working on algorithms that can classify these events and learn and say, you know what, those are seizures and the device isn't detecting those. Change the algorithms and put them back into the dogs without them ever coming into our office. Those devices are now implanted in patients at Mayo. We hope to be doing some here. And if you can imagine, it's not much more of a stretch to have your device retuned every time you walked into a Starbucks, rather than having to go to the doctors at 3-month intervals. Now, you know, if the stimulation setting doesn't work right, it might interfere with your coffee a little bit, but it's certainly a work in progress. There's a lot of interest in these data as well, and just our shared archive, open source, IEG.org, now has 5,700 people who are using the data worldwide in this map. So pretty interesting. There's also a lot of work going on in this cloud computing for devices and sharing and aggregating data. And so Joost Wagenaar was a postdoc in the lab, and he's now an assistant professor in the IBI, collaborates with Zach Ives, chair of computer science, and a number of other faculty here taking data up to the cloud. We hope to make this a place where data will reside, and eventually utilities like this will be where your data will go, out of your device, up to the cloud to be retrained. And then the other issue is, why shouldn't everybody who has a device learn from everybody else who has a device? Why shouldn't the measures of your stimulation and your response for tremor or obsessive compulsive disorder or dystonia be compared against every other patient who's gone before and say, you know what, you're like these 200 people, and this is what worked in them, and that's where we're going to start in you. And that's becoming possible. There are privacy issues, but people are dealing with it. So here's an example in 3 cases of output from a NeuroPace device up on Pensive that shows seizures that are detected. And it's not much of a stretch to say, if the patient can be informed what behaviors cause seizures, like stress or drinking, none of that, or staying up late, that not only can the device work better to treat those events, but informing the patient of what they're doing and how it affects their health. It's like a pretty amazing development. And I think this is becoming quite real. And a number of folks are working on this. And this is just an example. Every one of these horizontal lines is a day, a 24-hour period. This is output from a device we worked on to predict seizures before they occur. Blue means that it's predicted that you're going to be seizure-free for at least the next hour. Red means a seizure is likely. The lightning bolts means a seizure happened. Gray means there was a data dropout. And white means the device couldn't tell. This was the best patient out of the 15 in Australia that we worked on. But you can see that every seizure was predicted in advance. There were 3 or 4 false alarms in a month where the patient could take medicine to try to prevent the seizures. And what the patient said that they got the most benefit from was the blue. Because when they saw blue light on their device, it told them that they had an hour where they could be pretty sure they'd be safe to go to the store or go out to the theater or have dinner or something like that. This is today. This isn't like science fiction. This just gives you an idea. This is an output sent up to the cloud of measures in a patient with a NeuroPace device that we have over a 3-year period. And those are the kinds of data that we can extract to get features to compute on. There are problems. It's not continuous data. You know, Brittany used to have a lot more hair before she started pulling a lot of it out for this. But really interesting and capabilities to do tons. What about the medical record? Suppose your device, which has algorithms in the cloud, can get to your medical record. So this is work that Kevin Shea and some other folks are doing in the lab with Colin Ellis and Dan Roth in computer science, Collins in neurology. This is 12 years of data extracted initially from the records of 9,500 patients. There are only 5,000 that are displayed here. This is 12 years. A yellow dot says the patient was seizure-free, had a seizure since the last visit. Horizontal lines are individuals. Blue means they were seizure-free. Well, wait a minute. The device can look and see, did this patient take their medicine regularly? Maybe that's why they had a seizure. Is there something else that's going on? Did they show up for their appointments? Maybe they might suggest changes in stimulation or changes in therapy. But then, wait a minute, there are kind of privacy issues there too. But it's not hard for these algorithms to get access. Believe me, if Kevin can get access to your data, the algorithms can, and so can the insurance. So this is one of the things we're working on, and it's a work in progress, and it's a difficult problem because we don't have great implantables that can transmit data out in real time. But the idea is that we have patients with implants. Right now we're using patients implanted in the epilepsy monitoring unit with electrodes in place. Data's coming out, and it's giving off predictions of probability of seizure, characterizing the seizure. A chatbot is something we're working on to interact with the patient through regular surveys, but also so the patient can freely talk with the chatbot and say, I feel like I'm going to have a seizure. Or the device can pick up something that's going on in the EEG and say, what are you doing? Your probability is changing. And then develop this system where the devices can actually speak and communicate with the patients. Kind of interesting, you know, there's voice printing now where you can record your voice and have a computer synthesize speech in your own voice, or remember a parent's voice or something else. This device could actually communicate with you through the voice of your favorite teacher, your most feared superhero. I mean, it becomes kind of a weird thing to think about how your life might interact. And even with these simple surveys, some of the patients in the hospital were communicating with them like they were listening to them, like more than the nurses. So it could become kind of a weird part of your being. I don't know if you've seen this, but ChatGPT, this is one that just came out recently where this chat strategy from one of the AI companies was asked to write a biblical verse in the language of the King James Bible explaining how to remove a peanut butter sandwich from a VCR. And it did a really good job. And if you haven't seen it, I mean, it ends with, and the man heeded the Lord's words, and from that day forth he kept his sandwich in their proper place, and he was saved from trouble and woe. Amen. But if you have to live with this this chatbot, maybe it would take on kind of a personality for you. And you guys have probably all read about this poor scientist who spent so many hours with this thing. He thought it was sentient, and that's a little scary. So near the end, this is what my clinic looks like in 2035. 8 a.m., computer referral, predicted new onset seizure patient, forecasted seizure risk of greater than 85%, a perfectly healthy person. Should we implant a device in that because the computer accessed their medical records and said, you're going to develop epilepsy? That's scary. 9 a.m., medication-resistant college student. The implant shows poor compliance. She wasn't taking her meds. Drinking. The insurer is threatening to cut off their insurance. How stupid does that sound? Not very. 9:30, refractory patient for pre-surgical discussion. The computer optimized stimulation through the cloud hasn't worked. They're going to go for robotic ablation. 10:15, follow-up for regenerated graft to treat traumatic brain injury. Imaging cognitive map, similar to what you heard before from Desmond, shows improvement. We're going to adjust the stimulation and growth patterns. Then 11, wealthy patient's son is failing 8th grade. Parents want augmentation. They will pay out of pocket. Should I approve it? That's where we're headed. So these are decisions that you all are going to have to make. How much should we invest in this? What about the scientific payload? Should the data from every person's implantable device go up to the cloud and be available for everybody else? These algorithms and devices can learn and treat at scale, but what about freedom? Do you really want these devices? I can tell you can tell when you're drinking. Do you really want everybody else to know? Like what you're doing when? It's not so unrealistic. Is augmentation ethical? I don't know. Remember that guy Elon Musk? Would you trust him? Are those implants going to come preloaded with Twitter and Truth Social? Could be. We're going to have to decide these things. It's not science fiction. And I put up actually a reference to Anna Wexler, who we're going to have come and give some talk sometime. If you don't know her, she's a neurotechnology ethicist, which is, how cool is that? I don't want her looking at my stuff. No, that's not true. So this is the CNT, and you know, truth can be a little stranger than fiction. And I think we're headed here, and it's a very exciting time. So thanks so much.
So now we will be doing a quick, about 10 to 15 minute Q&A with all three of the speakers. We are actually bringing in chairs. I think the chairs are over there. They're coming in. Yeah.
Okay, is this?
Okay, it's on. All right, great. So if anyone has a question, you know, just raise your hand or say something, and Julia over here will bring the microphone over to you, so you can ask your question to our three speakers. And these questions can be, you know, related to any one of their talks individually, or it can be, you know, bigger picture questions for all three of them.
Okay. I don't know if it's wired into
Oh,
this.
let's go.
So I have a question for Desmond. You stated the reasons why you wouldn't do.
Check.
Oh, does it work? Working?
I didn't do that.
1, 2, 3. Okay.
See to check that.
Hello? No.
So you stated reasons for not doing DBS, et cetera. I'm really curious. What would someone who does DBS or any of these other modalities, why would they say that they are not doing TMS?
Why would somebody opt for DBS? TMS?
Well, you said this is why I'm not doing DBS. This is why I'm not doing ECT. So
Yeah.
for anyone who's specializing in those modalities, why would they say, and this is why I'm not doing TMS?
Oh, okay. So if you stay in the completely non-invasive world, right? Non-invasive imaging, non-invasive stimulation, the recordings have lower fidelity. They're like a little less crisp and accurate when you move out of the direct brain recording and direct stimulation world, right? So what does an fMRI signal tell you compared to a direct brain recording? It's a little looser, right? It's a little messier in the non-invasive space. So linking them together, though, where you have some patients who are getting DBS and recordings, electrical stimulation, recording from directly in the brain, and then taking those folks out after they've been explanted in the epilepsy monitoring unit, and then doing my piece on them with TMS fMRI. Linking these measurements together, I think, could tell us a lot. And working with Casey Tracy Halpern in neurosurgery and Kate Davis and epilepsy monitoring unit, linking these wonderful experts together who do invasive things with the things that I do. I think we can further expand and link them to the benefit of the patients who aren't eligible for the direct stuff.
So thank you.
Oh God.
It's like a White House press conference, you know?
Hello. So I guess I had a question for just the last talk, the hopefully dystopian future we might or may not be heading towards. And I guess I was kind of curious because you thoroughly convinced me that we're heading towards, I guess, a lot of questions ethically. And I think you profoundly threw it back to us as the audience saying, these are things that we need to ask ourselves. I'm curious, how is it that I can get better involved in helping? Because it seems like with technologies increasing at a rapid pace, that the only oversight that at least I'm aware of now is like legislative and legal action, and in some ways to change the ways that these companies and can interface with data usage and things like that. And it seems that with technology going faster and faster forward, that the speed at which those regulatory bodies would need to interface is too slow for harm to be done. I guess I'm not exactly sure what how I'm trying to ask. But I think maybe you get where I'm-
that was pretty articulately said, and I think it's maybe something that maybe each of us could address. You know, I'll take a crack at it at the beginning. You know, you all are academics. You know, the fact that you're still in training, and some of you may not be in training, some of you may be past that, but your opinion matters. You're educated scholars. And so I think there are a few things. First, writing in the academic space is important, and you can write and submit things to journals as groups, as individuals with your PIs expressing opinions. You know, there's a tremendous amount of interest in the use of AI. I don't know if you've followed some of the literature, but, you know, the use of it for profiling criminals at airports, for face recognition software, has been a huge problem, particularly with, you know, underrepresented minorities, African Americans, people with dark skin, you know, are nailed all the time as the wrong person and kind of roughed up and worse. So through yourselves and here at Penn, through your professional organizations, I think those opinions carry a lot of weight. And I think that's probably a great primary outlet. I don't know, do you have thoughts?
I mean, it's a philosophical.
I didn't help you. By giving you
That's
that.
being clumsy. It's a philosophical quandary. I mean, we went through this with the Patriot Act right after 2001 with the you know, World Trade Center going down and all of these kind of invasion in privacy that people took and accepted at the time because they said, well, this is for a larger cause or whatever. And then there was pushback. I mean, there was a lot of opinion, I think, at the time against it as well. But because of all of the stuff that happened, you know, other opinions prevailed. So I think there's always going to be a spectrum of opinion one way or the other. And a lot of it I feel like there's an ebb and flow with these sorts of things. And there is going to be a lot of pushback on certain things.
I think he asked, like, what can they do? And I think don't underestimate your power as scientists that are coming up. People listen, they need expert opinions.
And you are going to come across difference in opinions. And so I think as long as you are aware of what the other opinion is, and you can get some dialogue that you can reach, hopefully some sort of consensus, but it's really worrisome. I mean, I was thinking about that movie Minority Report,
Oh, yeah.
which is a bit freaky, right? And so how can you predict the future? I don't know. You don't know if you're going to be right or what do you want to risk, right? Like if you're at risk for a seizure, you don't want to just collapse. So there's a lot of ethical, philosophical things that a lot of people are thinking. I mean, it's way above my head, but it's really interesting that everyone is thinking about this.
I thought of something pretty different in terms of what you were asking. I understood that differently. So when you were asking your question, I was thinking you were asking, what can we do to translate science into clinical interventions more rapidly to help more people and not stall so long with the science developing? That may not be what you're asking at all, but
Talking dystopia, and you're like,
yeah. Sort of like politicians who have an answer prepared, and whatever question you ask, they're like, you're like, what the hell? Why did they say that? That's not what I meant. But yeah, I'm thinking of there's a lot of like when it comes to being a scientist and doing things that you hope will help patients compared to being a clinician where there's a person there and they need help right now and you need to like follow the best evidence and also for what the insurance is going to pay for and all these considerations that in some cases limit you and you feel like there's a promising intervention and there are pathways, especially for very sick patients, for patients with very rare conditions. There are pathways to getting like approval and following your best sort of evidence and judgment as a clinician that helps you kind of translate these things faster. But I think that there's a lot of like movement in the FDA approval process and people are hoping for better therapies to come faster. And I think, again, it's one of these balancing questions about for the average patient, what should we do? What should we do when we're kind of desperate and there looks like to be something we should try? And I think those are kind of different pathways that are both worth putting energy into.
should really make a throwable, like laser targeted.
We could try to make it happen.
I bet the guy up there would be very.
I kind of have a follow-up question to what Desmond was just saying. Do you think there's a lot of like clinical intuition on how to treat certain diseases, either with like stimulation or like adjusting medications that doesn't necessarily make it into the literature because people or clinicians at least are making those like quick decisions like, okay, I know that based on my research, this is more helpful than whatever the guidelines say. So they do it, but don't necessarily like publish it because it's not kind of like off label or like off the record.
I feel like this relates to kind of medicine and how it's practiced and the limitations and what's evidence-based and what's not, and how clinicians make decisions and share information with each other, which is more of Dr. Litt's, I think, knowledge base. But I agree there's important considerations there that following an evidence base, and there are a lot of practices that I believe would benefit from following better kind of data aggregations.
Yeah, I'll kind of address part of that too and say that there are a lot of problems with the way therapies make their way into patients. You know, currently, if something's not profitable, it's hard to get it through. I saw an example where there was a lot of trouble trying to figure out how to tell whether somebody's shunt was clogged. So, right, it's draining CSF through a tube that goes into the abdomen, and patients complain of a bad headache. And is the pressure elevated? Is the flow going? And so somebody thought of a device where they would just take an ice cube and put it over where the shunt tube crossed the collarbone, and it would cool the CSF, and then just used a digital thermometer, like a infrared thermometer, to see if the temperature changed in the abdomen, right? That's pretty smart. It costs nothing. They couldn't get the thing approved. And they finally got a version of it approved and invested in with a disposable like Peltier device that was like $150 a pop to cool the CSF here, right? And then some fancy thermometer with a disposable piece. So, I mean, there are issues about, like what you said, stuff that may work that's hard to get forward. And I think there are people working on these sorts of things, orphan devices and stuff like that, where industry might not want to pick them up. So, I mean, it is a problem, right? The current way that science gets forward into the public domain is a little bit flawed in some countries where medicine is for profit.
I also have a thought that's only tangentially related to what we've just discussed, which is trying to work with a device company to fund some of my research. And they say, well, how much does the individualized functional MRI guided brain stimulation really buy you? How much does it buy you compared to just find a spot on the scalp? It's about this far, zap it and see what happens, right? And from my perspective as a scientist, right, I want the best, the most accurate, the most precise, measure everything. From their perspective, they say, we want something that the clinics can take up without any fancy experts, like collecting MRI data and making these individual targets. So with the pushback between us, like pushing for this precision and pushing for something that is easy to implement, I think in some cases we'll find some middle ground where I'll say, well, it'll be based on a scalp target, but it's coming out of my research. So I like translate the MRI to an average and then put it in a kind of scalp target and see if that does better than what people are already doing with their scalp target. And maybe with the scalp target, we can also add some imaging so we understand the mechanism, even while we're still aiming to find something that the average clinic can do to help more patients. Because at the end of the day, we want to help more patients, and maybe the super individualized, precise guidance isn't always going to be necessary. So maybe we start with the scalp-based target for the patients who don't respond fairly quickly. Then it's worth the cost to the insurer, et cetera, to do the more precise, expensive, fancy kind of imaging technique. But having this pushback between the people who have to cough up the money or who have less expertise with the people doing the kind of high level science is sometimes a worthwhile discussion that can end up helping more patients at the end.
I had a question for you, if you don't mind. Sure. And so we see a lot. So that guy Dusk, who we were talking about, was mentioning 3 days ago about using Neuralink to help people function with spinal cord injury and do motor control. But your work made me really think that while that may improve their quality of life initially if they could restore some motor function, that these other autonomic derangements may kill them in the end regardless. So, I mean, what do we need to do for spinal cord repair and treatment?
So that's a great point. So if Kim Anderson, she's someone who's living with a spinal cord injury, but she's also a researcher. She surveyed people with a spinal cord injury and said, what do you want the research community to be studying? And, you know, most of the research, if you look at the literature, a lot of it is motor function, a lot of it is sensory function. But when you talk to people who are living with an injury day to day, they want, well, it depends on the level of injury. If it's a high level injury, they're quadriplegic, they do want some hand function because that will allow them some autonomy, right? Some independence. They're able to move in a chair, they can move the joystick, or they can, but if you take people with a lower level injury who are still paralyzed, their priorities are not movement, I mean, they would love it, but if they had to choose, they would choose these more basic fundamental quality of life functions.
Yeah, like bowel, bladder, sexual function.
Bowel, bladder, sexual function, autonomic dysreflexia, which is at extreme periods of hypertension because it just makes them feel horrible, and it's actually life-threatening. So, you know, kind of the take home from that is that you can talk to the people if you're doing biomedical research, think about who the end consumer is. I mean, people with spinal cord injury, they don't want to be called patients. They're individuals. They're just happen to have just a bad day, right? So they are living with the spinal cord injury and they are consuming whatever we could possibly give them. And so that's how they consider themselves. That's how they want to be referred to. And I think having that mentality when you're thinking about biomedical research, regardless of where you are on the spectrum, if it's pretty basic or it's just about to get into use in the clinic, think about it from the consumer point of view.
In the interest of time, we'll have one more question.
Oh my gosh, what an honor. Well, thank you so much. This question is for Dr. Litt. I know that a lot of folks would lean towards stereotactic EEG because it's less invasive and because ECOG has this dense coverage. I guess when I was seeing your slide on who should have it implanted, seeing ECOG, how are you going to make it less invasive? Or is there kind of a path towards that for ECOG?
Yeah, so that's a really key point. If I'd have showed that slide 5 years ago, I wouldn't have showed a stereo EEG electrode. I would have showed a grid or a strip going on a brain surface. And that's really fallen out of favor for the epilepsy world because the morbidity is so much higher. But there are a number of people making electrodes, some of them trained here, like John Viventi, who I mentioned before at Duke, Flavia Vitali here, and a number of other centers where they're making very small, flexible, kind of rolled up electrode strips that they can put in through small burr holes. And so I think for some applications where cortical surface electrodes, like Eddie Chang's work for speech synthesis, for example, you will see those kinds of less invasive surface ECOG arrays that are being used. There also is some other crazy science fiction stuff that's out there. So if you look at Paulina Anakeva's work, or even some work that Dave Isidore and Andrew Chalkas have done, there's work with delivering these constructs, liposomes, with nanoparticles inside of them, or very small particles that they inject in the bloodstream and subject them to an RF field in a zero in a big magnetic field. Picture putting somebody in a scanner, having a zero in a field where you want to deliver the particles. And when those particles, the blood goes through that area, those little liposomes with iron oxide particles in them rupture and deposit their payload right in that location. And so you will see non-invasive devices delivered across the blood-brain barrier that way. And there's even one grant that we were part of that used click chemistry. And the theory was you could deliver particles and build up devices in the brain that way, like you'd build the space station with like a module at a time. And so I think you're going to see a variety of different approaches to accessing brain. And I do think it's not too far away where people will look at what I did as a fellow in the early years with these huge craniotomies. In some places, they remove like a huge part of the calvarium, put it in the fridge, and have people with these huge electrode arrays mapping brain. We don't do that much anymore. And it's going to be looked back at like we look at using leeches, So I think hold on to your hat. It's changing really rapidly.
All right.
Did you say beer? Did you say beer?
Beer and cheese. So thank you guys all for coming out. And thank you to our three speakers. Again, give it up for them. That was some very interesting and inspiring work. So NeuroSciFi, the final frontier inside our heads, has been a production of the Neuroscience Public Lecture Series, which is run by a group of us from GLIA, which is the Graduate-Led Initiatives and Activities Committee, which itself is a group of neuroscience PhD students here at the University of Pennsylvania. GLIA has multiple initiatives, including outreach, community building, professional development, and action against bias. And broadly, the mission of Public Lecture Series is to both show the public the cool research that neuroscientists here in Philly do, and also what their tax money is going to funding. You can learn more about the Public Lecture Series and GLIA by going to www.upenglia.com. And you can also will be able to find a recording of this lecture later on YouTube and possibly other platforms. And now I think for the for the part most people have been waiting for, the reception outside where there is food, beer, and cheese. Thank you. Yeah, that was really cool. I think you have to go in from the top.
Oh.
Wait, did you? Okay, that's good.
Yeah.
Did we stop it?
Is that X?
Yeah.